various orders of reaction. We have the first one. We have zero order reaction. First order reaction. Second order reaction. So I was supposed to talk about this first before I talk about orders of reaction. So let's quickly talk about rate law. Please do now. Let's talk about rate law. So rate law, which is also known as rate equation, is an equation that relates rate of reaction to the concentration of reactant. It is also known as rate equation. It's an equation that relates the rate of reaction to the concentration of the reactant. Emphasis on the reactant. Okay? Now, for example, if I have a reaction A to B, right? My rate law is going to be R proportional to my A. Now, A raised to the power of X. This X is order of reaction. Right? This X is order of reaction. So when you introduce the equality sign and remove this proportionality sign, you introduce rate constant. So this is actually rate equation for this. Anytime this equation, it must be left hand side, it must be right hand side. So this equation now is relating the rate of each chemical reaction to the concentration of the reactant. Meaning that depending on the order of the reaction, if you increase the concentration of the reactant, your the rate also increase. That's the equation. Now this is actually for this reaction. What if I have for reaction like A plus B giving me C? We have two reactants here, so the rate law of this particular reaction is going to have two reactants. So this becomes R equals to A is constant, times concentration of A raised to the power of X times concentration of B raised to the power of Y. Please, it is important for us to know that this X and the Y are orders of reaction. So, if a reaction has just one reactant, which is this A here, and you write this rate law and raise it to X, this X is actually the order of the reaction because you only have one reactant here. Now, but what if in a case where you have two reactants, the order of this reaction is X and Y. So you cannot call X alone the order of the reaction, no? So in this case now, for the second reaction, X plus Y is what we call the overall order of reaction. Now this is for the equation 2. Now for this equation 1, this X you're seeing here is also order of this reaction because this reaction has just one reactant. But in the case where this guy has two reactants, you cannot just call one of them the order of the reaction. So in this case now, this X is order of reaction with respect to A. This Y is order of reaction with respect to what? B. Now when you sum both of them together, they will give you the order of the overall reaction. Or we call it the overall order of the reaction. Now it is from this order of reaction that gave rise to this zero order, first order, and third, second order. Meaning that if X plus Y is equal to 0, that becomes zero order reaction. If X plus Y equals to 1, that becomes first order. If X plus Y is equals to 2, that becomes what? Please, this X plus Y, remember I said, it's only X plus Y because we have two reactants. In a case where we have just a single reactant, this X is the order of the reaction. So if X in this case is equal to 0, this guy is a zero order reaction. If x in this case is equals to 1, is the first order. If x is equals to 2, is the second order because we just have one power here. Okay? Okay. Possible question. The possible question they asked in past question is said the sum or the total of the powers to which the concentration terms are raised in the rate law, which is meant to be rate law. It's called the order of the reaction. You may want to ask, what is the summation? Of course, what I just explained now, right? This x was the order of reaction with respect to A, the y was order of reaction with respect to B, the equation I gave us previously, right? So now, both of them, they will raised as a power on those concentration terms. So this is another way question can be asked. The sum or the total of the powers to which the concentration terms are raised in the rate law is called that. What's the answer? Order of reaction. Just in case. I think these formulas should be used for calculation. So I just want to give us, for zero order, I'll give us the integrated rate law. I'll give us the half-life, and then I'll give us some few notes about that. So we have for zero order, now the integrated rate law is so if you look at this, now this is the formula for integrated rate law of zero order reaction. So meaning that if you want to carry out calculation under zero order reaction, this is the integrated formula. A naught is the initial. Imagine a case where they give you A naught, they give you the time, and they give you rate constant, and you have to find the final concentration. This is the formula I'm going to make use of. Now, there's also what we call half-life. Half-life is the time it will take half of the initial concentration of the reactant to react. I repeat, half-life is the time, the same if they say, please look up. Half of 10 is how many? So if something has concentration of 10, half of 10 is 5. So the time is going to take 5 out of this 10 to react. Is what we call the what? Half-life. So if you want to define that guy, we say half-life is the time it will take half of the initial concentration of the reactant to react. Or the time it will take 50% of initial concentration to react. So just in case in exams, you're asked to solve for half-life of a reaction. And that reaction happens to be zero order reaction. This is the formula I'm going to make use of. How would you know it's a zero order reaction? That will tell us when we are done with all the formulas. The rest of them. Now this is the rate law for zero order reaction. Remember, rate law for a simple reactant, here is going to be x. If x is equal to 0, this becomes zero order reaction. And you can actually agree with me that anything raised to the power of 0 is always equal to what? 1. So it is important for us to know that they will ask you, the reaction occurs as a rate that appears independent of the concentration of the reactant. What it means is that in zero order reaction, I do not need concentration to know my rate, because concentration has no contribution to this guy, because this guy is raised to the power of 0. So if you increase this concentration to 1 million, it's not going to affect the R. So just take note, in case you're being asked which order of reaction that has a rate that appears independent of the concentration. Class, which order of reaction is that? Obviously, you can see it here. X is equal to 0, so anything raised to the power of 0 is 1. So the real Rate's law for zero order reaction is this. So there's no concentration here. Can you see that? Okay. So let's look at first order reaction. They are integrated formula, half-life, first order. Integrated Rate's law. Now that's the formula for integrated Rate's law. Now for that of zero order reaction, if you notice the formula I gave us previously for zero order reaction had final concentration, initial time, and rate constant. The only difference here is the arrangement of these formulas. So whether it is zero order, first order, or second order, these parameters must be present. However, the arrangement differs. Okay, so for the half-life of a first order reaction, half-life of a first order reaction is T half equals to 0.693 all over K. Now let me split this. Please look up. There is also an important key point we need to note down here. Alright, the key point is that if you look at the formula of this half-life for first order, let's circle this guy. This is for first, this is for half-life, and this is integrated formula. Some lecturers might decide to use lane. So this formula can decide to say or, can say lane AT equals to lane A naught minus KT. If I'm using lane, I won't put this 2.303. Right? That's different because this is what differentiates log from lane. So take note of this. You can use this very well, or preferably for students, use this. Now, but please take note of this. Half-life of a first order reaction is independent of the concentration. It's actually kind of confusing with what I gave us previously. In zero order reaction, for zero order reaction, the rate is independent of the concentration, right? For zero order, because zero order reaction is R, K, A naught. Anything raised to the power of 1, 0 is 1, right? So for zero order reaction, the rate is independent of the concentration. But for first order reaction, the half-life, look at this half-life formula. Can you see anything like concentration here? No. So for first order reaction, the half-life is independent of the concentration of the reactant. Don't mix it up with the other guy. Now, so this is actually the formula for integrated Rate's law, the one you're going to use to carry out calculation. Remember I earlier explained this guy. This AT is actually final concentration. This A naught is initial. This is time. Now, I've given us three formulas. Listen and listen very carefully. This K is actually rate constant for second order. Now, the unit of this rate constant is actually what is going to differentiate one rate order of reaction from the other. The formula here, if you notice the formula here, the parameters involved here are 4. In all the 3 orders of reactions, we have them. We have final, we have initial, we have time, and we have rate constant. Alright? Alright, so I say I had to make it this way to make it very systematic. I gave us 6 formulas in total. 3 integrated rate laws and 3 half-lives. Now, when do we make use of those rate laws? Those integrated guys? I say identify which order of reaction they are referring to. Identify which order of reaction they are referring to, not are they referring to. So, now how do you identify that? It's either they will mention it in the question, or the unit of the rate constant is going to help you to do that. Oftentimes, they used to mention it, and some other times they will not. So they will actually expect you to just use the unit of the rate constant and get your order of reaction. Okay, so I'm going to give all the different units of orders of reaction, and then we solve. Now look at this. I said one of the ways you can actually identify order of reaction is by the unit, if they don't mention it in the question. Please, let me state this. This capital letter M is molar. Molar means mole per liter. Take note of that. Now for zero order reaction, the unit of zero order reaction is always mole per liters per second, which is molar per second. The unit of first order is per second, and the unit of second order is per mole liters per second. Now let me state this. In as much as time is actually presented in seconds here, they might decide to use other units of time. They can use it to be per minute. They can use it to be per, here can be minutes, here can be minutes. Now remember, I told us that when I gave us those integrated formula, I say T is time. Now listen. Anytime you are asked to carry out calculation, your time, the unit of your time should always correspond to the one in the constant. If you are being given mole per liters per second, it means that your time is in what? Seconds, right? So whichever calculation or parameters you are being given to, if the time is not in seconds, you must convert it. If they give you time in minutes in this formula, this constant, your time in your calculation should be in what? Minutes. Because you cannot come and start changing the constant. This is a constant for a reason. So all your parameters must correspond to that of the what? Constant. Alright, so take note of this unit. Alternatively, you can use the general formula. We say mole per liter 1 raised to 12, 1 minus n as the power per second. Now, n is the order of reaction. If n is equal to 0, or let's say if n is equal to 1, first order reaction. How do we, let's see if we are going to arrive at this. If n is equal to 1, 1 minus 1 is what? 0. Everything here raised to the power of 0 becomes 1, right? 1 times this is per second. So that's how we got this. If n is equal to 0, that's first order reaction. 1 minus 0 is 1, right? Anything raised to the power of 1 is still that stuff. So we have mole per liter times our per second, which is what we have here. Right? So that is actually how the unit of these guys can be identified. So I'm going to give us a question here. It is left for you to tell me the order of the reaction based on the unit of the rate constant. And once you've identified the order of the reaction, you use a formula, get the answer. We have two questions here to answer. Right? They didn't mention whether it is first order, second order. Please look up. We have a question here. Now remember I told us that most of the times they will actually tell you whether a reaction is zero order, first order. So I'll leave them to that. But for this particular question, I did not in any way mention whether it is a first order or a second order reaction. But from the nature of the question, you can tell. Anytime you see half-life, rate constants, just know that, take your minds back to order of reaction. Alright, so look at the first one. They said, calculate the amount of 0.8 mole per liter ammonia left after 300 seconds. If the rate constant is 2.66 times 10 to the minus 3 mole per liter per second. And also calculate the half-life. First, which order of reaction is this? Zero order, right? Please, based on this unit of the rate constant, remember I told us that the unit of the rate constant will actually go a long way in helping us understand whether it's zero, first, or second. Now, this unit is that of a zero order reaction also. Now, say the unit is that of a zero order. So we have our K is 2.66 times 10 raised to the power minus 3 mole per liters per second. Now, we are asked to find the amount that is left after 300 seconds, meaning that we are asking you to find the final concentration. This was what they gave us at the start of the reaction, but we are told that the reaction lasted for 300 seconds. Now, solve for what is left after 300 seconds. So I'll come here, my initial becomes 0.8 mole per liter. Now, this is initial concentration. Now, the final is what I am asked to find. And of course, they gave me time to be 300 seconds. And since we have agreed that, or since it is very obvious that this guy is a zero order reaction based on this unit, we're going to use our zero order rate integrated rate constant rate law, which says that A naught minus AT equals to what? KT. Now this is actually zero order integrated rate law. AT is what I'm asked to find. So I'll bring AT to the right hand side and bring this guy to the left hand side. In other words, I want to make this guy subject of the formula. So when I do that, this becomes AT now we have this to be 0.8. The unit corresponds, so there is no need of solving with the unit, minus our K is 2.66 times 10 raised to the power minus 3, and our T is 300 seconds. 0.798. So you realize that at the back. I'm sorry about stressing you. So the final answer here, which is the final concentration, is 0.002 mole per liter. So we have, please, it's still for this first one because we are asked to solve for the half-life as well. So what's the formula for half-life of a zero order reaction? All over 2K. Where K is our rate constant. And of course, our rate constant was given to us to be equal to this. So this becomes, our A naught is the initial concentration. This becomes 0.8 all over 2 times 2.66 times 10 raised to the power minus 3. Now this becomes, if you solve it, it should give you 149 something. When you approximate, it's 150 seconds. Please look up. Now, which order of reaction do we have here? First or second? This is first order. Because the unit of the rate constant is per seconds, right? So because of this unit is a first order reaction. So I'll say B, this is a first order reaction. It is a first order reaction because of the unit of the rate constant, which is per second. So therefore, the rate constant here is 87 per second. Now the A says if the initial concentration of cyclobutane is 2.0, so my A naught is 2.00 molar. What is the concentration after 0.01 seconds? Now, AT is what I'm asked to find. Now, T is 0.010 seconds. So, based on the fact that this guy is a first order reaction, I'm going to make use of my first order formula, which says log A naught. Now let's solve this guy. I'll say now this guy is so if you press the calculator, this bracket is 0.37777. Now log 2.0 is 0.8. So when you actually evaluate that, we have minus 0.07674. Now this is what we're going to have, but then you're asked for your 80, not the log. Now for me to get my 80, please, you're not going to take the anti-log of this guy. So this becomes anti-log of minus 0.07. Now when you do that, once again was 0.84 molar. Now this is actually what remained after 0.010 seconds. Okay? What fraction has decomposed? Hello, please look up. What fraction has decomposed in this time? Now, for something to have decomposed, it means how many have reacted. Initially, our final concentration is 0.84 now. This was what they gave me, and this is what is remaining. That means what has decomposed is also subtracted from this. Right? Amount decomposed, I'll say B. Amount decomposed or reacted is 2.0 minus 0.84, 1.16 molar. This was not decomposed or reacted. Now they said fraction. Now fraction decomposed is equals to amount decomposed all over initial. Please look up. Assuming they had said in percent, if they had said what fraction decomposed in percent, I will say what here? Times 100. Take note of that. So this becomes 1.16 all over 2.0. So if it was in terms of percentage, in percent would be 0.58 times what? 100, that is equals to what? 58%. The C says we should solve for the half-life. Now, half-life of a first order reaction is always 0.693 all over K. So this is what you're going to do. 0.693 divided by our K is what? 87 per second. Please, what's the answer here? Effect of temperature on rate of reaction. Decrease or increase in temperature affects the rate of the chemical reaction. Of course, if you could recall, factors affecting rate of chemical reaction, temperature is there. If you increase the temperature, right, you increase the average kinetic energy of those particles, making them to collide faster. So increase in temperature or decrease in temperature affects rate of a chemical reaction. Fine and good. Now it has been proven experimentally that for every increase by 10 degrees, rate of reaction is doubled. If you increase it by 100, of course 2 times 10, it goes like that, right? So for every increase of 10 degrees Celsius, experimentally it has been proven that reaction rate will always increase by 2, right? Or it will double. Now, this young man here, Arrhenius, proposed an equation that relates temperature and rate constant, right? Now, if you take the log of this guy, or the lane of this, we're going to have this. But the ones you guys are going to be making use of is this guy. Now, for two temperatures, T1 and T2, and two rate constants, now this equation can actually becomes this. Now, this law is actually taking care of this. So, for example, if I want to carry out this, I'll first of all get my value here, get my value, solve for it, and take the log. This log is affecting up and down. So this log K over K1 equals to energy of activation, or activation energy. Now, like I said, apart from the R, that is a constant, we have 5 parameters, 1, 2, 3, 4, 5. Okay? They can ask us to solve for any one of them, any of them. Most common is always either of K1 or K2, right? Sometimes you can also ask us to solve for EA, that's activation energy. So we're going to take 1 or 2 questions and then see how we're going to apply this formula. Now they said the activation energy of a reaction was found to be 52.04 kilojoules per mole. If the rate constant at 40 degrees is this, what is the rate constant at 55 degrees Celsius? Now the initial temperature, the rate at the initial temperature becomes the initial rate constant. And how do you know the initial temperature? Of course, the one that will always come first, or most of the times from the question you will know. So here, our energy of activation is 52.04 kilojoules per mole. Now anytime you're solving something, right, and you need to insert the parameters, don't actually insert kilo. Kilo is not a unit. Kilo is a multiplier. So I need to take this guy to joules. So for me to remove this kilo, I'll multiply with 1000. So this becomes 52.04 times 10 raised to the power of 3 joules per mole. Alright? Now, my T1 is 40 degrees Celsius, which is 40 plus 273. Please, 40 plus 273 is what? 313. Please, you must convert it to Kelvin. So the reason why we actually added 273 is for us to convert it to Kelvin. Now, K1 at this T1 is 5.76 times 10 raised to the power of minus 3 mole liters per second. Okay? Now, moving forward, now this gave us T2 equals to 55 degrees Celsius, which is 55 plus 2. Please multiply, add this up for me. 328 Kelvin. Now, they asked us to solve for K2. Now, K2 is what they asked us to solve for. So I'll say log K2, K1 equals to EA R Please remember it is 1 minus T1, 1 over T1 minus 1 over T2. Now, just ignore this. I'm asked to find my K2. So I'm just ignore this side first. Let's solve everything on the right hand side first. So this becomes equals to my EA is 52.04 times 10 raised to the power of 3 all over this is 2.303. Now recall this R is a constant. R is a constant 8.314 joules per mole per Kelvin times 8.314. Now this is 1 divided by, my T1 is 313 minus 1 over, my T2 is 328. So everything here, if you press it, it will give you 0.397. Everything on the right hand side. So you have to please first attend to the brackets. Attend to the bracket. Whatever answer you have, multiply by this numerator and divide by this. If you have your natural display calculator, you can just press everything at once. Right? So this is log K2 over K1. Now, since I want to solve for my K2 class, right, if I want to actually remove K2 here, first I need to take the anti-log so that I can get rid of this log. And for me to get rid of the log, please don't divide both sides by log. Take the anti-log. If you take the anti-log of this, if you take anti-log of this, K2 over K1 becomes anti-log of 0.397. Now this is equals to 2.4952. How do you get your anti-log? Shift your log, then you press what you have inside the bracket. Okay, so this is now what we have. So it's more like saying K2 over K1 equals to 2.4952. Now recall I was asked to solve for my K2. So I can now make K2 subject of the formula. It becomes K1 times 2.4952. Now if you actually solve this guy, K1 was given to us to be equals to 5.76 times 10 raised to the power of 3. Now times your 2.4952. Now K2 now becomes equals to 1.44 times 10 raised to the power of minus 2 mole per liters per second. Now the unit is going to be equivalent like that of the first one. It has to be the same. You don't have to stress yourself for the unit. Whatever the unit of the first rate constant was, of course the second guy will have to keep the same formula.